let's work out some example using the divergence theorem. So first of all, we have a problem that's returning from section 16.7. We did this problem, it was the last problem that we worked out in that section. We evaluate the surface integral of this vector field over this tetrahedron. So remember, if we draw out our axes here, we essentially just got the tetrahedron that was in the corner. And doing the surface integral was a little tedious. We had 4 different surfaces that we had to integrate over because we had 4 different faces of the tetrahedron. It wasn't too bad because they are definitely all planes, but there's quite a bit of work involved. However, with the divergence theorem, we can actually do just a single triple integral, and it makes it a lot easier. We're going to integrate the divergence of f. Remember the divergence, we take each of the components and differentiate with respect to the corresponding variable. So here, for the x component, we differentiate with respect to x, the y that's sitting there. Then we differentiate with respect to y, the z minus y that's there. And we differentiate with respect to z, the x that's sitting on our in our z component. Of course, there's no x's in y, and there's no z's in x, so both those are 0. The z here goes away as well. So we're just differentiating negative y, which turns into a negative 1. The divergence of this vector field is actually really simple. If we integrate that over the tetrahedron, we get that the surface integral is equal to the triple integral over this tetrahedron. We can call that E, or we can call it T for tetrahedron, of negative 1 dV. The tetrahedron, so keep in mind the surface on top here is z equals 1 minus x minus y, because it's x plus y plus z equals 1 is the surface that goes through, is the plane that goes through 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we'll integrate eventually over z, going from 0 on the base to 1 minus x minus y. We're integrating that over the triangle that's down here in the plane. That triangle the x is going from 0 to 1, y is going to go from 0 out to this line, and that line is y equals 1 minus x. So the integrand is really nice. The limits aren't quite as nice, but they're not too bad. Go ahead and get into it. So integral of negative 1 with respect to z is negative z. So we essentially get to replace z with 1 minus x minus y. I'm going to use the negative there to actually swap the order of these. So I'll have x plus y minus 1. Then we get to integrate that with respect to y. We get y, or let's do xy plus 1 half y squared minus y from 0 to 1 minus x. Now we do get to plug in 1 minus x for every y and simplify. That involves a little bit of algebra, which I'll go ahead and skip over. But we end up getting a negative 1 half plus x minus 1 half x squared. And of course, integrating that, we get a negative 1 half x plus 1 half x squared minus 1/6 x to the third. Going from 0 to 1, well, of course, we get to plug in 1, we get negative 1 half, positive 1 half, those cancel out, and then minus 1/6. And that's our answer. And that was exactly the same answer that we got when we looked at the surface integral. We saw that when we did the different surfaces, the ones that are on the coordinate planes, those all came out to be negative 1/6. And the one over the z equals 1 minus x minus y, that one turned out to be a positive 1/3. And that positive 1/3 canceled out 2 negative 1/6, leaving a single negative 1/6 overall. So we get the same thing with a lot less work. Moving on to problem 6 from this section. So here we have another vector field, uh, and we're looking at a surface, or we're wanting to integrate this over the surface where we have a box enclosed by the planes x equals 0, x equals a, y equals 0, y equals b, z equals 0, and z equals c. So they don't give us what those numbers are. It turns out we don't really need to know them to work this out, though they will be in our final answer. We draw a picture of this. I'm going to go ahead and draw this into the... So that means this one's... Here's our x, back here's our y. We're just looking at the boundary of this box. We go down to the origin, and we go out to A on the x-axis, B on the y-axis, and C on the z-axis. Now, integrating over this box would be kind of annoying, because we have 6 different faces. At least some of them are coordinate planes, and others are parallel to the coordinate planes, but it's still a lot of steps. It's still 6 different integrals, and we have to worry about orientations for each of those surfaces, and all of that. Instead, we can just do a triple integral over the box. If we look at the divergence of f, so here we actually have to differentiate all these functions with respect to their corresponding variables. And you don't always have to write this all out. I'm just doing it just to demonstrate what's going on. Derivative of, with respect to x, of x squared yz. Of course, the yz there is just treated as a constant. It's just tagging along. The x squared becomes a 2x. Same thing here. The y squared becomes a 2y. We still have the x and z. And finally here, the z squared becomes a 2z, and we still have the x and y. Of course, they've made this so it actually combines nicely. So these actually all are like terms. So we get a 6xyz. If we integrate that over the box, then by the divergence theorem, this surface integral is just the triple integral over the box. We can go ahead and call that b for box, of 6xyz dv. Now, our limits here are just going to be from 0 to a, 0 to b, 0 to c. We can make it simpler on ourselves by kind of splitting this up. So this is just the product of a function of x, a function of y, and a function of z. So we can just integrate those parts with respect to their corresponding variables. We'll pull the 6 outside. But we have the integral from 0 to a of x dx, integral from 0 to b of y dy, and the integral from 0 to c of z dz. Of course, the integral of x is 1/2 x squared, which we'll evaluate from 0 to a. That just turns into 1/2 a squared. Same thing for y. We get a 1/2 b squared. And for z, we get a 1/2 c squared. Well, one of the 1/2s can cancel out the 2 from the 6, so we get a 3 there. But we do have 2 other 1/2s, so we get a 3 over 4. A squared, b squared, c squared. And it's as simple as that. If we were to look at the surface integral, this would have been way more complicated. Go ahead and move on to problem 7. Here we have another vector field. We want to find the surface integral over the boundary of the solid with the cylinder, y squared plus z squared equals 1, bounded between the planes x equals -1 and x equals 2. So if we go ahead and plot that, in fact, let's go ahead and use GeoGebra for that. So our cylinder was y squared plus z squared equals 1. Then we're bounding that between the planes x equals -1 and x equals 2. So we're just looking at this part of the cylinder. And we want to find the surface integral over that. Now that would have 3 different parts to it if we wanted to do this as an actual surface integral. Of course, we're not going to be doing that. We're going to be using the divergence theorem. So here, first we need to take the divergence of f. And I'm just going to keep writing this out just to help you guys out. So the derivative with respect to x of 3x y squared, the x goes away, we just have a 3y squared. There's no y's in x e to the z, so that goes away. That's one of the advantages of doing things with the divergence theorem, is sometimes parts of your actual vector field don't involve some of the variables, so they just go away. The derivative of z cubed with respect to z is 3z squared. We can actually even pull out the 3. We have 3 times the quantity y squared plus z squared. And that's actually kind of useful for us, because if we want to integrate over the inside, this is a cylinder. It would be nice if we could use cylindrical coordinates. Of course, this is not a vertical cylinder. We're going to have to use coordinates of r, theta, and x instead of r, theta, and z, but it's really just the same kind of idea. And the fact that our divergence is essentially just going to be 3r squared doesn't hurt. So the integral over the surface of f dot ds, of course, is the integral over the cylinder. I'll call it, I don't know, I'll go ahead and call it E. Calling it C would be kind of weird when we've been using C for curves. Of 3r squared. Well, actually, let's leave it as in terms of y and z for the moment until we actually put this into our cylindrical coordinates. So we get the integral over. So theta is going to go from 0 to 2 pi. We are going all the way around the cylinder. The r is going to go from 0 to 1 because that cylinder has a radius of 1. And then, of course, our x values are going to go from -1 to 2. Our integrand, we have a 3r squared. Remember, when we use cylindrical coordinates, we do have an extra r. Then we have dx for that. We have a dr here and a d theta. Now, this only involves r in the middle. So we don't have any x's, we don't have any thetas. We can go ahead and turn the integral over from 0 to 2 pi of theta into 2 pi. The integral over dx, this part will just turn into the difference between these. We have a 2 minus a -1, which we'll simplify in a moment. And we have the integral from 0 to 1 of, well, actually, let's go ahead and even pull out that 3, I guess. We have an r cubed dr. So 2 pi times 3, that'd be a 6 pi. 2 minus -1 is 2 plus 1 is another 3. So 6 times 3 would be 18 pi. But then this turns into a 1/4 r to the 4th. So that 1/4 is actually going to change that 18 eventually. That is going from 0 to 1, which essentially just means we have 1 minus 0. So this whole integral turned into a 1/4. 1/4 of 18 pi is a 9 pi over 2. And that's all it is. Not too much work overall there. Just we need to know how to set it up. All right, for our last problem, our last example, we're going to look at problem 14. Here we have a vector field f equals the square of the magnitude of r times r, where r is just our regular position vector given by xi plus yj plus zk. We're going to integrate that over the sphere with radius r centered at the origin. So if we need a picture of that, we can go ahead and get one. This is our sphere. Now, we can actually write out f easier just by remembering that the magnitude of this is just the square root of x squared plus y squared plus z squared. Of course, with it being squared here, we don't have the square root. So we have x squared plus y squared plus z squared times xi plus yj plus zk. Or in other words, if we multiply these out, our first component is going to be an x cubed plus xy squared plus xz squared, and other terms. So we'll have essentially the same thing for the j and k. But I'm not going to write it out because we're going to, just to save a little bit on space. Of course, we're going to be using the divergence theorem here. We could actually integrate this over the sphere itself. That actually probably wouldn't be too bad. But let's go ahead and do what they say. So we're taking the derivative of f with respect to x, or derivative of the first component of f with respect to x. So we're differentiating x cubed plus xy squared plus xz squared. The second component with respect to y, that is x squared y plus x cubed plus yz squared. And then finally, our third component with respect to z, we have an x squared z plus y squared z plus z cubed. Derivative of this is 3x squared. We have a y squared. We have a z squared. From here, we have an x squared. We have a 3y squared. And we have a z squared. Finally, here we have an x squared, a y squared, and a 3z squared. And, well, we have x squareds, we have y squareds, we have z squareds, and in fact, in all cases, we have 5 of them. We have a 3x squared, we have an x squared, and an x squared. So 5 of those. Same thing for y, same thing for z. I'm going to go ahead and pull out that 5. Of course, since we are integrating, we're going to be integrating this over the interior of a sphere. That kind of begs spherical coordinates. And our integrand here, the function that we're trying to integrate, is really set up for spherical coordinates. This 5 times the sums of these squares is just going to be 5 times rho squared. And so we integrate this. So we're integrating f dot ds over the sphere. It's going to be in spherical coordinates. Remember, theta goes from 0 to 2 pi. Phi goes from 0 to pi. R is going to go from 0 to the radius. In this case, that's r. They didn't give us an actual value for that. We're going to be integrating 5 rho squared, but we also need our additional factor of rho squared sine phi. Of course, we don't have any thetas, so that the integral from 0 to 2 pi of that just becomes a 2 pi. The integral, so we can go ahead and split this up over phis and rhos. The integral from 0 to 0 to pi of sine of phi d phi, and the integral from 0 to r of 5 rho to the 4th. This time I'm going to pull out the 5 because, well, 5 rho to the 4th is very nice and easy to integrate. Integral of sine is a negative cosine. Integral of 5 rho to the 4th is simply rho to the 5th. So when we plug in pi, we get a -1, so we get -1, so +1. Then we subtract, so we get rid of the negative there as well, and cosine of 0 is 1. Basically, this turns into a 1 plus 1. So we'll end up just multiplying 2 pi by 2, we get a 4 pi. And then this one, we get an r to the 5th minus 0, so we just have r to the 5th. So it wasn't too bad. Honestly, though, we probably didn't actually save too much work by doing the divergence theorem here, because we actually know stuff about the sphere already. We do know for the sphere using the outward orientation that unit normal is going to be essentially just r over r. So this is xi plus yj plus zk over the radius. Remember, we need it to be unit normal. The x squared plus y squared plus z squared is equal to r squared on the actual surface S itself. And so we're pointing outwards directly away from the origin, but we have to normalize it to make sure it's a unit vector. We also would be using our parameterization of phi and theta. Remember, in that case, first of all, we get the normal here, but we also, when we turn this into a surface integral, the easiest way of doing that would be taking our function, our f here, which is the magnitude of r squared times r, dotted with that normal, which is r over big R, over S. As long as we are actually on S itself, the magnitude of r is just capital R. So this is actually a capital R squared. R dot R is actually magnitude of R squared again. So we end up getting R squared, capital R squared. We have another capital R squared, but dividing by an R, we end up getting R cubed over the surface. And that is a scalar surface integral. But when we actually parameterize this, remember we have phi and theta, so we'll go from 0 to 2 pi on theta, 0 to pi on phi. We have r cubed in here, but then we also need the magnitude of r phi cross r theta. That's part of doing our scalar surface integrals. And we saw that in this parameterization, this parameterization based off of spherical coordinates, this is actually going to just be r squared sine phi. Then we have d phi, d theta. Of course, here we end up with an r to the 5th. We don't have any thetas, so we end up with a 2 pi times r to the 5th times the integral from 0 to pi of sine phi d phi. But as we just saw back here, that integral turned into a 2 overall. So we end up getting to multiply this by 2. We get 4 pi r to the 5th. Just like we got when we did it as an integral of the divergence over the inside. Now, the only thing here is that we would have to remember all the stuff about the parameterization of the sphere and how that interacts with the radius of the sphere. It might just be easier to do it this way, even though this did involve actually having to take the divergence first. So, at least in this particular case, either way would actually be not too bad. Unlike our other ones where, so this one would have turned into 3 different surface integrals. This one would turn into 6 different surface integrals. When you actually save yourself on the actual surfaces involved, it does save you a lot of work. So that's our last problem that we're going to be doing for the semester, in fact. We do have our final exam coming up next week, and if you haven't signed up for it already, you're now assigned to Tuesday. So either let me know if that doesn't work for you, if there's a major problem with doing that, or whatnot. And I will have my office hours next week as well. But that's the end of our videos. So I'll see you at the final.